Hello students, welcome back to today's class on similar triangles, and we are in lecture number 2 in that. In the last class we discussed what are similar triangles and we discussed about the basic proportionality theorem. Once again for 1 or 2 minutes let's have a small recap and then we'll move forward for the converse of basic proportionality theorem, right? So my name is Avinash and I'm a graduate from IIT Kharagpur. Let's start today's class. So what we have learned in the last class is basic proportionality theorem. If a line is drawn parallel to one side of a triangle, this line is drawn parallel to one side of the triangle to intersect the other two sides in distinct points, okay? So these 2 points, then the other 2 sides are divided in the same ratio. That means the ratio of E dividing AB and the ratio of F dividing AC is the same. That means AE by EB is equal to AF by FC. So this is the basic proportionality theorem. Okay, these are in proportions. When we say ratios are equal, we say that they are in proportion. Okay, so AE, EB, AF and FC are in proportion. That's the reason we say that basic proportionality theorem. Right? So now let's try to discuss more about this one. Converse of basic proportionality theorem. What do we see? That in basic proportionality theorem, what we had discussed, a line is drawn parallel. And if that is drawn, then we have this ratio. But now, in the converse of that, we have a different statement. If a line divides 2 sides of a triangle in the same ratio, now, we are not mentioning that this line is parallel. But if this ratio is same, if the line divides 2 sides of a triangle in the same ratio, this ratio AE by EB and AF by FC, these 2 ratios are same, then the line is parallel to the third side, and the line EF is parallel to BC. Okay. So in basic proportional theorem, we are saying that this line is parallel, and then we are telling that these 2 are in proportions. Now we are saying that they are in proportion, and then we are saying that these 2 are parallel. That is a converse or the reverse of the basic proportionality theorem, which we say converse of basic proportionality theorem, right? So let's try to have some discussion based on that. So we have a question here. What value or values of x will make DE parallel to AB in the given figure? So DE parallel to AB. So this DE parallel to AB, not AB, it should be BC. Okay, DE parallel to BC, right? What value of x will make DE parallel to BC in the given figure? AD is equal to 8x plus 9. AD is equal to 8x plus 9. CD is equal to CD. Okay, see, there is a mistake here. Maybe D should be there. One second, let me check that. DE parallel to AB. All right. I think there is a problem with the diagram. Let me solve that again. Once again, let me draw the line. Let me draw the diagram first of all. What values of x will make a DE parallel to AB? So in the figure, so let's just try to draw the figure. I'm so sorry. So DE parallel to AB. So this is AB, let us say ABC, and we have DE. We have DE parallel to AB in the given figure. AD is given and CD is given. I think this is correct. Okay. So AD is given as 8x plus 9 and CD is given as x plus. The given figure which we have shown you before is not exactly correct. And BE is given as 3x plus 4 and CE is given as x. So now using basic proportionality theorem, as it was given to make DE parallel to AB, in order to make them parallel, these 2 should be in proportion. Right? So that means x plus 3 by 8x plus 9. X plus 3 by 8x plus 9 is equal to x by 3x plus 4. Okay, x plus 3 by 8x plus 9 is equal to x by 3x plus 4. So if you now try to multiply this one, x plus 3 into 3x plus 4, x plus 3 into 3x plus 4 is equal to x times of 8x plus 9. X times of 8x plus 9, correct? So x into 3x is 3x square plus 4x plus 3 3s are 9x plus 4 3s are 12 is equal to 8x square plus 9x. Okay, so now let's try to solve this clearly. 3x square plus we can cancel 9 and 9, that will be more easy. So 4x plus 12 is equal to 8x square. So try to bring that 3 other side and all the terms other side. So we'll get 8x square minus 3x square minus 3x square minus 4x minus 12 equal to 0. So 8 minus 3 is 5x square minus 4x minus 12 is equal to 0, right? So 12 5 is 16, right? So 12 into 5 is 16. So now I'll tell you how to factorize this one. You already learned how to factorize a quadratic, right? So 12 into 5 is negative. That becomes minus 60, which we can write as 10 into 6. As we have negative 4, we keep it as minus 10. Okay, so we'll get 5x square minus 10x plus 6x minus 12 equal to 0. So taking 5x common, we'll get x minus 2 plus 6. If you take common, again it is x minus 2 equal to 0. So we'll get 5x plus 6. Let me write it here. 5x plus 6 into x minus 2 is equal to 0. But x cannot be a negative number because we have CE is x. X should be a distance. X cannot be negative. So x is equal to 2 is the correct value. X equal 2 is the correct value. If you want to verify, it's very simple. Just substitute x equal 2 in the given instructions. Okay. So 2 plus 3 is 5. 8 to the 16. 16 plus 9 is 25. So 5 by 25 should be equal to x is 2. So x is 2. So 3 to the 6. 6 plus 4 is 10. If you can carefully observe, 5 by 25 and 2 by 10 both are equal to 1 by 5. So we can say that they are in proportion. And if they are in proportion, we can say that that given line is a parallel to AB. And for that, the value of x is 2. 5x plus 6 cannot be the answer because it gives a negative minus 6 by 5. Negative number cannot come because we have x as a distance from point C to point E. Right? It's a very beautiful question. Just try to apply the basic proportionality theorem properly and you'll get the answer. Okay. Next one. Right? In triangle ABC, DE is parallel to BC. Find the value of x if AD is equal to x, DB equal to x minus 2, AE is equal to x plus 2 and EC equal to x minus 1. Once again, in triangle ABC, DE is parallel to BC. Now it's correct. Find the value of x if AD is equal to x, AD is equal to x, DB is equal to x minus 2, AE is equal to x plus 2 and EC is equal to x minus 1. EC is equal to x minus 1. Correct? So now you need to apply basic proportionality theorem because it was given that these two are parallel. Right? If these two are parallel, the things will be in ratio. So we know that using basic proportional theorem, AD by DB is equal to AE by EC. So AD by DB means x by x minus 2 is equal to AE x plus 2 by x minus 1. So now let's try to calculate that. Cross multiply. X into x minus 1 is equal to x plus 2 into x minus 2. X into x minus 1 is x square minus x is equal to x square minus 4. Okay, so I think we can cancel x square on both the sides. So we'll get minus x is equal to minus 4 and x is equal to 4. And in case if you want to verify, you can verify that easily. Just substitute that values. Okay, x equal to 4. So 4, this value is 4. 4 minus 2 is 2. Although this dB is less, it's okay. Okay, don't worry about that. Here, again 4 plus 2 is 6. 4 minus 1 is 3. So 4 by 2 and 6 by 3. Are these two equal? Yes, these two are equal to 2. It is enough to say that they are in ratio. It is enough to say that they are in ratio and from there we can directly get that. Okay. So, moving ahead for the right. In the given figure, LM is parallel to CB. LM is parallel to CB and LN is parallel to CD. Prove that AM by AB is equal to AN by AD. A very beautiful concept, a very beautiful application. Carefully see here. In the given figure, LM is parallel to BC. It was given that this line LM is parallel to BC. I think in this triangle ABC, we can use basic proportionality theorem. In the triangle ABC, we can use the basic proportionality theorem. That becomes, if you use basic proportionality theorem ABC, we can say that AM by MB is equal to AL by LC. Is equal to AL by LC. Okay, as these two are parallel. That is the first thing we can bring from this theorem. And the same way again, this side also for this triangle, this ACD triangle. Okay, so again this will be in proportion if you carefully observe. So AL by LC is equal to AN by ND. AN by ND. Okay, so this is with respect to triangle ACD, this one with respect to triangle ABC. Correct? Now, if you carefully observe, these two are equal. AL by LC and AL by LC are equal. So we can equate these two. From there, we'll get AM by MB. AM by MB is equal to AN by ND. Okay. But still, we have a small confusion here. AM by AB is given. AM by AB, the total side is given. It's okay. Basic proportional theorem you can apply in both the ways. I'll tell you the other way. Even this is correct. But to get the exact result, what is being asked, I'll tell you how to do that. Right. So now, AM by AB, the complete length, AM by AB is equal to AL by AC, the complete length. AL by AC, even this is basic proportionality theorem. Even this is also basic proportional theorem. The same way with this, in the lower triangle, we get AL by LC. AL by LC is equal to AN by ND. Is equal to AN by ND, right? So now, if these two are equal, we can equate these two. That will give you AM by AB is equal to AN by AD. Sorry, AN by AD. This should be AN by AD. So that is what we need to prove. Understand? AM by AB, AN by AD. Right? So let's move forward for the next one. Prove that a line drawn through the midpoint of one side of triangle parallel to another side bisects the third side. Once again, let's try to understand that. Prove that a line drawn through the midpoint of one side. Let's try to take this as the ABC triangle. From the midpoint with, let's say D, we are drawing a line one side of triangle drawn through the midpoint of one side of triangle parallel to another side. Bisects. Okay, we need to show that this bisects each other. Let us take E. Now, as it was given that these two are parallel, we are drawing parallel, you can use basic proportional theorem. If these two are parallel, they will be in proportion. Right? Converse. If they, see, actually what is the concept? If this ratio is same, we say that this line is parallel. But now, in the converse way, if the line is parallel, we can say these two ratios will be equal. And one more beautiful point is given, we are drawing through the midpoint. So that means AD by DB, both are equal. It was given that it is a midpoint, right? So AD by DB is equal to AE by EC. Correct? So AD by DB, as these two are equal, we can say that AE is equal to AE equal to EC. Sorry, AE is equal to EC. Okay, so AE and EC. So this one and this one are equal. These two are equal. Okay. Now, what we need to prove that a line drawn in the midpoint of one side of triangle parallel to another side bisects the third side. Yes, it is bisecting. Because it is a midpoint. It is dividing the equal ratios. If this is 2, this is 2. If this is 20, this is 20. They are in the same ratio. So we can say that E bisects AC. That's it. It is enough that we have proved. Correct? Clear. Next one. Prove that a line joining the midpoints of any two sides of a triangle is parallel to the third side. Prove that a line joining the midpoints of any two sides. Of triangle is parallel to the third side. Let's try to understand that. A line joining the midpoints of any two sides. So these two are midpoints. So line joining the midpoints of any two sides is a parallel to the third side. This is A, this is B, this is C, and this is DE. It was given that it is moving through midpoints, right? So if it is midpoint, AD by DB will be equal and AE by EC will be equal. AD by DB is equal to AE by EC. So using basic proportionality theorem, we can say that it is enough to say that the side is parallel to the third side. Okay, so DE is parallel to BC. DE is parallel to BC. It's enough. Basic proportional theorem has a lot many applications, not just one or two. We have a lot of applications based on this. Let's move for one more question based on this basic proportionality theorem. What is that? AAA criteria for similarity of triangles. In the congruency of triangles, which you have learned in the lower classes, we discussed about SAS, ASA, AAS, so different types of congruencies. And again, I told you in the last class, there is a small difference between congruency and similarity. Okay, so we'll discuss about that. AAA criteria for similarity of triangles. So what is that given? In two triangles, corresponding angles are equal. Corresponding means if this is one triangle and this is another triangle, if this angle and this angle, those are corresponding angles. Okay. Corresponding sides, then the corresponding sides are in proportion and hence the triangles are similar. And the corresponding sides are not, we're not saying about equal, because we cannot say equal. That comes with congruency. We're not talking about congruency, we're talking about a similarity. Similarity of the triangles, okay? If two triangles, if corresponding angles are equal, if these two corresponding angles are equal, for example, x and x, then the corresponding sides are in proportion, and hence the triangles are similar, right? All the sides and all the angles. Okay, so next what we can learn here, identify the similarity of the triangles in given figure. We need to identify the similarity here. So this 40, 60 and 80, this is 80, 40 and 60, right? So here if you can see similarity, which two angles are similar? 40 and 40, right? And again 60 and 60, 80 and 80. Are these two similar? Yes. As we have all the three angles same. This is ABC, this angle ABC, this is a PQR. Angle ABC, this is PQR, okay? So for angle A, for angle Q, both are same. Angle A is equal to angle Q, right? Angle B, which is 60, is equal to angle R, which is 60. Angle C, which is 80, is equal to angle P, which is 80 degrees. So we can, from all this information, we can say that these two triangles are similar. I don't say they're congruent. Congruency we're not talking about. We're talking about a similarity of the triangles. There is a difference between these two, right? Next one. Identify the similarity of the triangles in the given figure. We need to find the similarity. So you can say one right angle is here, and here also we have one right angle, correct? Right angle and right angle. And so if you carefully observe, okay, identify the similarity of the triangles. Let us say this is x, this angle is x, vertically opposite angles, even this value is x. Vertically opposite angle, that is also x, okay? Now if this is 90, this is x, the remaining will be 90 minus x, because the sum of all the three sides is 180. So even this will be 90 minus x. So we can say that all the triangles, all the things are equal, right? So all the angles are equal. So using A similarity, we can say that these two triangles are similar. These two triangles are similar, right? So moving ahead for the next question. SSS criteria for similarity of the triangles. SSS, what is that? Side, side, side. Side, side, side. Okay, let's move that. In two triangles, if corresponding sides are proportional, then the corresponding angles are equal, and hence the triangles are similar. Once again, see that corresponding sides are proportion. See, we are talking about proportionality. We are not talking about equal. In congruence of triangles, we talk about equality, but here we are talking about a similarity. So they need not be zero. They need not be equal. If corresponding sides are proportional, then the corresponding angles are equal. Then the corresponding angles are equal, right? Corresponding angles are equal, and hence the triangles are similar. And hence the triangles are similar, correct? If in two triangles, if corresponding sides are proportional, then the corresponding angles are equal, and hence the triangles are similar. So this is a SSS criteria. This is SSS criteria. Okay. So this one triangle, I'll take one more triangle. Okay. All of these two are not equal in shapes. But if their corresponding angles are equal and the corresponding sides are in proportion, we are not talking about equal sides. These are not equal sides, but still they are similar if their proportions are same. That means if this side is 3 and this side is 6, if this side is 4, this side is 8, let's try to see that, okay? So definitely we can say that they are in proportion, and the angles should be equal. Angles cannot be different. When we're talking about similarity, angles will be same, okay? Next one, SAS criteria for similarity of the triangles. What do you mean by SAS criteria? Side, angle, side. In the previous one, we discussed about SSS, which is side, side, side. Here it is SAS, side, angle, side. And when I say side, angle, side, you cannot take any angle, whatever you want. You need to take two sides and corresponding angle to that, okay? If one angle of a triangle is equal to one angle of another triangle, and the including sides of these angles are proportional, then the two triangles are similar. And the two triangles are similar, right? So let's try to take one triangle, let's try to take one more triangle. Okay, we are discussing about SAS, right? So this one more small triangle. Now, SAS states that the side, angle, side. So this is side 1, this is side 2, and this is the angle. Again, side 1, side 2, angle. Sides should be in proportion always. Sides should be in proportion. Angles are also proportional, including sides of these angles are proportional. If one angle is equal to one angle of that triangle. Okay, so this angle and this angle are equal in both the triangles, and these two are in proportions. S1, S2 as side 1, side 2 in both the triangles. If they are in proportion, then we can say that the triangles are similar. The given triangles are similar, right? Moving ahead for one more. What is the next one? Identify the similarity of the triangles in the given figure. We need to find which triangles are similar, right? So let's write once again. Identify similarity, right? So if you carefully observe, here we have 2 plus 3, 5, 2 plus 3, 5, and this side is common for both the sides, both the triangles. That side is common for both the triangles. If I take this as A, B, C and D, E, if you consider triangle ABC and triangle ADE, so now our aim is to find whether these two are similar or not. ABC and ADE. For ABC, if you can observe, one side is 2 centimeters and the other side is 2 centimeters. For triangle ADE completely, one side is 5 centimeters, other side is 5 centimeters. So correspondingly proportional, 2 by 5 and 2 by 5 both are equal, and one angle is common for both the triangles. Angle A is common for both of them, right? So based on this, we can say that based on SAS, right, side, angle side, we can use that these two triangles are similar. Okay, so in the coming class, we are going to have a more discussion about all these triangles and more discussion about similarity of triangles, and don't get confused with the similarity of the triangles and congruency of triangles, right? Thank you so much, students. Stay tuned to get the next lecture. Thank you.
Hello everyone. So now we'll be discussing about scattering of light. Right, until now we have learned about reflection of light, refraction of light and dispersion of light as well. So these are the phenomena. So the new phenomena that we'll be discussing about is scattering of light. Okay, so my name is Shashin Reddy. I'm a graduate from IIT Dhanbad. Let's go into the class. Now, scattering of light is so important because there are many phenomena in nature that occur because of that. And very simple example is this. Sky is blue, clouds are white. Now why is that? Why is the sky blue? Why are the clouds white? Why are the rain clouds dark? And all of them happen because of what? Scattering of light. So that's what we have to understand. And another simple example or some experiment you can call it. You can look at that here. See that here. Here you have a laser light and here you have two glasses of different liquids. In the first glass, if I call this as the first glass, can I see the laser beam? I cannot see the laser beam. But when it comes to the second glass, we can see the laser beam. The laser beam is visible. Laser is visible. So light is passing through it and we can see its path. Its path is visible to us. Now how does that happen? That also can be explained through scattering. Important, right? We'll go into it. So what exactly is scattering? So in scattering, what happens is, when light falls on tiny particles, it's not about like complete a big object, we talk about particles, very small particles, you can think of them as molecules, dust particles, right? Very, very small. So when light falls on those tiny particles like atoms, molecules, dust, etc., they absorb the light and re-emit it in all directions. This is known as scattering. So here, let's say this is an atom or a molecule or a particle, but a very small particle. Now when light is incident on it, now what does that particle do? It absorbs the light. Okay, it has absorbed the light. After absorbing, it will emit it. It has taken it in, it will also give it away, absorbing it and emitting it. But when it emits, in which direction? It can emit in any direction, right? It's up to it now. It can emit in this direction, this direction, this direction, this direction, this direction, this direction, towards us, into the screen, any direction. But in which direction does it emit? What it does is, it does not select, it emits in all the directions. The emission happens in all the directions. So it's like It is scattered away. It is scattered away. Light fell on the particle and then it has been scattered away in all the directions. It's like carom board. Right, all the coins are placed at the center. If you hit it, what happens? The coins scatter away. The coins scatter away. The same thing happens here. Understood? In scattering, what happens? Light is absorbed and emitted in all the directions. And emitted in all the directions. So it's completely different from reflection, refraction, or dispersion for that matter. Yes or no? When we talk about reflection, light just bounces back. Light just bounces back and in a single direction, as you can see. Light bounces back in a single direction. Yes or no? That is reflection. So here, it is completely different from scattering. In scattering, it is in all the directions, randomly. Then in refraction also, what happens? Light is not absorbed per se. Light is not absorbed. It just changes its direction. It changes its direction when it enters. This is refraction. Right, and these two phenomena are completely different from scattering. And now that we also have the knowledge of dispersion, we also have the knowledge of Vibgyor. That white light is made up of 7 different colors, right? Violet, indigo, blue, green, yellow, orange, and red. Vibgyor. Now the question is, we'll go back to the first question that we had. Why is the sky blue? Now we discussed that it is because of scattering. Okay, that's fine. But only blue color is scattered. If I am seeing blue, if I am seeing the sky as blue, blue is coming to us. Blue is coming to us. Right? So why is only blue color coming to us? Why is not, let's say, red coming to us? Right? So in scattering, it depends on what? It depends on the color of light also. The question, do all colors of light get scattered? All of them get scattered, but some get scattered more, some get scattered less. And it depends on what? It depends on the particle size. It depends on the particle size. That's what you have to be careful about. Got it? Okay. So before that, there is one thing again we have to remember. So let's revise it quick. Wavelength. Wavelength of colors. Basically, when I say colors, I am talking about Vibgyor only. So when it comes to the wavelength, which of them has the least wavelength? Which of them has the least wavelength? Violet or red? Which of them has the least wavelength? Violet has the least wavelength. Something you have to remember, everyone. Whereas red has the longest wavelength. Or else in place of least, if I go with shortest wavelength, it will be better. So violet has the shortest wavelength, whereas red has the longest wavelength. And obviously, in that order, wavelength increases. Wavelength increases from violet to red. That's important for us to understand. Why? You'll understand. Got it? Remember this. Now again, coming back to this, scattering depends on the particle size. So when I say particle size, there are different particles. Yes or no? Let's say, I'll take air for an example. In air, you have gas molecules. We have nitrogen, we have oxygen. Yes or no? These are the predominant gases in air, nitrogen and oxygen. So you can think of them as small particles. So for our discussion, these are very small. Understand them. These are molecules. We can't even see molecules using our naked eye. They will be very, very, very small. Whereas, when we talk about dust particles, let's say water droplets in the cloud. Right, on these we will be considering as larger particles. Okay. See, even dust particle is very small. Even dust particles will be very small for us. But when you compare the molecules of nitrogen, oxygen and dust or water droplets, in that comparison, nitrogen and oxygen, their molecule size is considered as small particle for scattering, whereas dust is considered as a larger particle. Now this difference is very important for us. Why? Because when it comes to smaller particles, shorter wavelengths are scattered more. Okay. So if light is incident, let's say on a nitrogen molecule, light is incident on a nitrogen molecule, then which light will be scattered more? The shorter wavelength. And what are shorter wavelengths here? Shorter wavelength is towards violet. So these type, violet, indigo, blue, these are the colors that will be scattered more because of what? Because of nitrogen. Because of nitrogen, you can say violet, indigo, blue. Those are the shorter wavelengths. But when it comes to larger particles, then what will larger particles do? They will scatter all the colors equally. All I can say is scatter all wavelength equally. Right? So how the scattering happens? Which light will be scattered, which light will be scattered more will depend on the size of particles. Will depend on what? Will depend on size of particles. That's what is written here. Very small particles, oxygen and nitrogen molecules, these are present in air. They are part of atmosphere. That's why we have taken oxygen and nitrogen. Yes or no? Scatter light of shorter wavelength more. Scatter light of shorter wavelength more. Whereas if I come to this point, larger particles, colloidal particles, what are colloids? You have learned that in chemistry. We'll also be going into that later on. So colloidal particles or particles in a cloud. When we say particles in a cloud, cloud is made up of water droplets, ice crystals, dust particles, all of them. Okay, so comparatively they are larger particles, and what do? They scatter all the wavelengths equally. So these 2 points are very, very, very important. This one and this one. And the second point is very simple. The same relation. Scattering of longer wavelength of light. When I say longer wavelength, you can think of it as red color. It increases with the size of particles. Simple. Okay. Good. Understood? Simple. So very small particles, they scatter light of shorter wavelength. Larger particles, they scatter all the wavelengths equally. Understood? Good. So the same points are written here, small particles and large particles. You can go through them. Based on this itself, different phenomena occur. Right? We'll go into that. But again, there is something called as Rayleigh scattering. So Rayleigh is a scientist. Rayleigh is a scientist. This, see here, Rayleigh's scattering. This is applicable for smaller particles. When I say smaller particles in your brain, you have to imagine nitrogen, oxygen molecules, smaller. Right, so for smaller particles or for scattering from smaller particles, the intensity of light scattered will be inversely proportional to 4 to the 4 or the 4th power of wavelength. It will be inversely proportional to the 4th power of wavelength. That is, and that's experimental. Okay, Rayleigh got it from experiments. Understood? So intensity of scattering will be inversely proportional to this. You have to remember that. And the same point will be mentioned here. The intensity of scattering of light has been found to be inversely proportional to the 4th power of wavelength, and this is known as Rayleigh scattering. The same statement is given here. Now some of you might be thinking, sir, what is intensity? What is intensity? Understand this. When we talk about intensity, the official term, the scientific definition will be energy per unit area per unit time. So it measures the amount of energy released in a unit area, in some area and in some particular time. Rate of energy released or rate of energy absorbed. Okay, but when we talk about intensity, we are talking about the amount of energy, rate of energy. So when we talk about intensity of scattering, you have to understand it as what? The energy of scattering, how much energy of light is scattered. How much energy of light is scattered, and it is inversely proportional to the fourth power of wavelength. Now what is the importance of this? Very simple. When it comes to wavelength, we understood that wavelength of violet is the least. Wavelength of violet is the least, and we have just seen that intensity is inversely proportional to the fourth power of wavelength. Inversely proportional, focus on that. What does inversely proportional mean? That means if one quantity is larger, the other quantity will be smaller. Right? Yes or no? So here, for whom will the intensity be greater? For which color will the intensity of scattering be greater? Inversely proportional. So for intensity to be greater, wavelength should be lesser. And for whom is the wavelength less? For whom is the wavelength less? Violet. That means intensity of scattering, obviously, or I can just say, or in simple terms I'll write, scattering of violet light. Okay, I'll write violet will be much greater than scattering of red. If you compare violet and red, whichever has the least wavelength, the smallest wavelength, the shortest wavelength will be scattered the most. That's why I told you it's important to remember the relation of wavelengths between all the colors. Got it? And that's the importance of Rayleigh scattering. For smaller particles, the intensity of scattering is inversely proportional to the fourth power of wavelength. And the point we just discussed, wavelength of red is greater than wavelength of violet. Right? Greater wavelength will mean less scattering. So red light is scattered the least. Red light wavelength is more, so scattering will be less, inversely proportional. One more, the other less. And violet light, because its wavelength is less, it will be scattered the most among the colors VIBGYOR. Among the colors VIBGYOR. So again comes an interesting point. Obviously, it's important. Got it? Okay, good. So let's come back to a simple question here. Which light is scattered the most among the options given? And in the options, what are the options? Indigo, blue, yellow, orange. We do not have violet, we do not have red. So we are not talking about those two colors, but the other colors here, indigo, blue, yellow and orange. So which is scattered the most? I'll give you how much time? I'll give you 30 seconds of time. So please try doing it. 30 seconds. Start solving it, everyone. Use Rayleigh scattering and use the relation between wavelengths. Sorry. Use Rayleigh scattering, the principle of Rayleigh scattering, okay, and the relation between wavelengths. So 3, 2, 1, and the time is up. Now let me explain. So first of all, it's important to understand the relation between the wavelengths, right? So when we go into the colors, VIBGYOR, which has the least wavelength or shortest wavelength? Violet has the shortest wavelength, and hence from violet the wavelength increases. Got it? So here, here what are the colors we have? Indigo, blue, yellow and orange. Indigo, blue, yellow and orange. So among these four colors, which one has the shortest wavelength? After violet, who has the shortest wavelength? Indigo. So among the options given, so among, I'll just write I for indigo, B for blue, Y for yellow and O for orange. Among these four colors, the four options that are given to us, indigo has the least wavelength. Indigo has the shortest wavelength. And because intensity of scattering, according to Rayleigh scattering, what happens? Intensity of scattering is inversely proportional to the fourth power of wavelength. So if wavelength is less, intensity will be greater, right? Indigo is scattered the most. Indigo is scattered the most. Very simple. So everyone, if you remember this, the relation between wavelengths and the Rayleigh scattering formula, you will get the answer for everything. At least the questions that will be asked to you. Got it? So and hence, which is scattered the most? Indigo is scattered the most, and the answer is option A. Option A. Good. Let's continue. So scattering of light is the reason behind many phenomena, many natural phenomena per se. So one such phenomena is called something called as Tyndall effect. Then the other phenomena is called blue color of the sky. Then we have reddish color of the sun. When we have white and dark color of the clouds. And then we also have red light as danger signal. There are many more, but we will be discussing about these one by one. Okay. So let's first discuss about what the Tyndall effect. Now, have you any time observed or watched anything similar to this, where you can see the path of light? See here, this image. Can we clearly see the path of light? Yes, we can clearly see the path of light. Even here, the path of light, and even in this case. So, path of light is clearly visible. Now, why is the path of light visible? Why? Because what happens is, just a minute. See, now air will contain dust particles, yes or no? Air contains dust particles, simple. So when light, and we'll say sunlight, and what is sunlight? Sunlight is white light, remember. Sunlight is white light. White light in the sense it contains VIBGYOR. So when white light is incident on, let's say, dust particles. So first thing that you have to think about is the size of the particles. The first thing that you have to think about is what? Size of the particles. Let's say these are dust particles. Dust particles in air. Now, dust particles small or large? Dust particles, are they smaller in size or are they larger in size? We discussed that dust particles are generally larger in size when it comes to scattering. So these are larger particles, you can say larger particles. And what do larger particles do? How do they scatter? They scatter light and all the colors of light. They scatter all the colors of light. So from here, you can see all the colors of light are scattered equally in every direction, by the way. So from wherever the light is passing, right, so look at this, from this dot, light will be scattered in every direction. It will also come to us, and when it comes to us, we see, light is coming to us, that means there is something there. Okay, so light is scattered along the path in which light travels. And for us to see something, understand this, for us to see something, light should come to us. For us to see something, light should come to us. So when light passes through and it is scattered, that light will come to us and we will see the path of light. And we will see the path of light. So what is the reason behind it? The reason behind it is scattering of light by larger particles. And which color is scattered? All the colors are scattered equally. You can say all the colors are scattered equally. Because larger particles, all the colors are scattered. Understood? That is the reason. So here it's a very simple one. Scattering of light by particles such that the path of light becomes visible, and that phenomena is called as Tyndall effect. So wherever the path of light becomes visible, which phenomena is that? Tyndall effect. And that Tyndall effect is again because of scattering. So it's not something special, it's nothing but scattering of light. Clear? Good. So here you can see that here. So in colloidal solution, you might have learned about colloid. Okay. So what happens in a colloidal solution? So if you take a colloid, the main feature of colloid will be there will be particles suspended. It might be a solution, that's fine. But in the solution there will be suspended particles. Yes or no? In very simple terms, I'm just giving you a very simple explanation. The exact definition of colloids, you have learned that in what? You have learned that in chemistry. So there are what? There are suspended particles. See here, there are different cases. One is when you take a true solution, as in this case. What is a true solution? There are no suspended particles, it is completely dissolved. Like when you add, let's say, salt to water, it will be completely dissolved. It will be a true solution. But when you have particles suspended like this, when we have particles suspended like this, and what do you call that as? You call it as colloidal solution. You call it as what? Colloidal solution. So are there particles here? We can clearly see that there are particles in the solution. And when light passes through it, what happens to it? It gets scattered. It gets scattered in every direction. Light gets scattered. And by what? By larger particles, because generally in the solution, a colloidal solution, the particles will be larger. The particles will be larger. So here when light passes through this, we cannot see the path of light because it is not being what? It is not being scattered. No scattering in this case. If there is no scattering, you can't see it. But here there is scattering. So if light is scattered, scattered light will come to us and we can see it. See, for us to be able to see anything, understand this point very carefully. If you want to see anything, or if you have to be able to see anything, that from that object, whatever it is, light should come to us. If light does not come to us, we cannot see it. That is the basic understanding. So if there is no light scattered, light will not come to us. But here, because there is scattering, light will come to us and we can see it. Okay. So this is also a part of Tyndall effect because you are able to see the path of light. So path of light cannot be seen when it is passed through a true solution because there are no suspended particles. But it can be seen in a colloidal solution because there are what? There are suspended particles which scatter the light. Got it? Good. So we have again come back to the same example that we were discussing at the beginning. Here there is no light, no path of light. Path of light cannot be seen. I'll just say path cannot be seen. But here path can be seen. What does that mean? That means here in the first case there is no scattering of light. But in the second case there is scattering. Simple. So wherever there is scattering, you should be able to see the path of light. Okay? Good. I hope you understood that. So here you can clearly see the solution on the right one is this, is a true solution where no scattering takes place, and the left one is colloidal because scattering takes place. As simple as that. Tyndall effect is causing light beam to be visible in the left case. Tyndall effect, or in simple terms, scattering. Tyndall effect, or in simple terms, scattering. Is that clear? Good. So in the same way, there are many other things, we'll go into them, but before that, let's complete Tyndall effect. Scattering of light by particles such that path of light becomes visible. That is Tyndall effect, we learned about it. The dust particles present in air are larger in size and hence scatter all the wavelengths of light equally. Yes, we have discussed these points. Okay, good. So now we have to go into blue color of the sky. We'll discuss that later on. Okay, in the next class, we'll discuss the rest of the phenomena involved with scattering of light. Okay, so for today, thank you. Thanks a lot.